section is going to take a look at the relationship between the surface area and volume of a sphere, and will be presented by myself, Nick Boxall, and Jacob Hilton. Firstly, we will be taking the formulas currently on the screen as they are given. Under initial inspection, it is immediately clear that the surface area is equal to the first derivative of the volume taken with respect to r. This presentation will, however, delve deeper into the connection between these formulas, as we aim to discover how the relationship of a three-dimensional sphere's surface area with its volume may relate to similar calculations with spherical objects in higher dimensional space. Initial formulas for both the contained volume and surface area of a 3D sphere were derived by Archimedes. In brief, Archimedes discovered that the volume of a sphere is 2/3 of the volume of the cylinder that encloses it. And given that the volume of the cylinder with the height 2r is 2 pi r cubed, the volume of the sphere contained within must be 4/3 pi r cubed. However, this formula can also be derived using calculus to sum an infinite number of infinitesimally small disks which are stacked and centered around the x-axis from -r to r. Similarly, Archimedes derived the formula for the surface area of a sphere by discovering that it must be equal to the lateral surface area of a cylinder. The lateral surface area of a cylinder is 2 pi rh, so where the height is equal to 2r, the area is equal to 4 pi r squared, which is therefore also the surface area of the sphere.
Proof in lower dimensions. As the definition of a sphere is all points equidistant from a singular point, a circle is a two-dimensional sphere as it is all points at a set distance from a central point on a 2D plane. As most high school students will know, the area of a circle is pi r squared and the circumference is 2 pi r. Deriving the area with respect to r clearly equals the circumference, and therefore this relationship holds true. Geometric proof. There are many proofs for the relationship between volume and surface area, but I think this one is the most interesting and the easiest to see. Take a sphere of radius r and add dr to the radius. dr is infinitesimally small and will allow us to see the change in volume when the radius is changed. Next, we are going to squash the sphere until it becomes a cylinder with only the height of the drs remaining. It's a little weird that the edge of the cylinder is square, but at the height of which the cylinder is, the difference between the square edge and the rounded edge is negligible. We want to measure the change in volume when adding dr, so we will bring out the volume of a cylinder formula, which is the area of the base of the cylinder times its height. The height of the cylinder is given by 2 times dr, as there was a dr on the top and on the bottom of the original sphere we had. And because we squashed the sphere, the total surface area of the sphere is located on the two bases of the cylinder. This means that the area of one of the bases is half times the surface area. While some of the sphere is located in the height, it's only the infinitesimally small dr, and therefore it is not included in our calculation. Summing these values into the volume of a cylinder formula gets a half times the surface area times 2 times dr. Cancelling out the half and the 2 and dividing by dr gets the answer that dv dr equals the surface area.
Proof in higher dimensions. Now, to prove that this relationship still occurs in higher dimensions, we're going to look at how it's still a first derivative. So we'll start with the base formulas of a sphere, which are volume and surface area, and then we're going to take the derivative formulas down the bottom of the screen. Now, here we apply the derivative formulas to the sphere formulas, and we see the formulas representing a surface area and volume in n dimensions. While the formulas still show the relationship, they cannot be counted as proof until it's shown in higher dimensions. However, as the formulas showed, you cannot solve volume or surface area without the other. However, math as it is makes life easier with its recurrences. Looking at lower dimensions, with a radius of 1, we can gather these three sets of values for volume and surface area. Now we begin to see a pattern or recurrence. This pattern is that surface area in n plus 1 dimensions is equal to 2 pi times that of the volume in the nth dimension. Now with this relationship shown, we can start to prove the relationship in higher dimensions. So we'll start with that pattern and apply it to surface area in the third dimension. We see here that we get surface area of 2 pi squared. Now, if we go to the fourth dimensional volume and apply this surface area to the formula we created earlier, we will see its volume. Now that we've proved it 1 dimension higher than a sphere, could we go even higher? Well, of course we can. It's math. So, in fourth dimensional surface area and fifth dimensional volume, we'll apply the formulas again. And as you can see, the relationship still is there. And this relationship will continue to apply as you see the diagram on the right. As you can see, the relationship between volume and surface area of a sphere is held up in higher dimensions. On the right, in red, you will see the original relationship, followed by the 2 dimensions upwards, which uphold surface area being the first derivative of volume, and therefore prove the relationship in higher dimensions.
Okay, thanks very much guys, well done. That was pretty good.